Hello there. Today we're going to concentrate on this integral rule. The integral of du over u is the ln of u plus c. And we're going to really focus on how we identify logarithmic form. There are really two things you need to notice here. One is that the variable is in the denominator and it only has an exponent of 1. This is essential for logarithmic form. If there is any exponent here other than 1, you will not have a logarithm after integrating. And the second thing to note is that in the numerator, you will have a multiple of the derivative of that denominator. So here we have u, here we have du. Okay, so it's important to take the derivative of that denominator and ensure that you have a multiple of it in the numerator. So those are the two conditions for logarithmic form. Okay, let's have a look at some examples. Okay, so this one is exactly that. Here we have the variable. It has an exponent of 1 in that denominator. What's the derivative of x? It's simply 1. So we have a multiple of 1 here. In fact, if you like, you can rewrite this just like that. The integral of dx over x is ln x. So we end up here with 5 ln x plus c. Okay, in fact, this second one is also a very simple example. This is like our u in the denominator and it has an exponent of 1. What is the derivative of 3x minus 1? It's 3. Up top, we do have a multiple of 3. We have the number 1. Okay, so what we have here is 1/3 of the ln of 3x minus 1. I mean, if you wanted to actually use substitution here, you can. You'd say that u is 3x minus 1. So du is 3 times dx. Okay, so we don't have up here 3 times dx. So what we actually have is 1/3 of du in the top, and in the bottom is our u. Okay, so we end up with 1/3 ln u plus c, and that is 1/3 ln of 3x minus 1 plus c. Okay, so in number 1 and number 2, the derivative of the denominator was just a constant. It was 1 and 3 respectively. Here, we still have a binomial in the denominator. The exponent on the binomial is 1. Okay, so we can make u equal to 6 minus t squared. Do we have a multiple of du in the top? So du is 0 minus 2t. So du is negative 2t. Do we have a multiple of that up top? In fact, we do. We have t. Here we have negative 2t. So we have negative 1/2 of du in the top. Okay, so because we have t and not negative 2t, we have negative 1/2 of the du in the top. The u to the power of 1 is in the bottom. So the exponent of 2 is only on t. So what we're saying is overall, that binomial certainly does have an exponent of 1. All right, so we end up with negative 1/2 times the ln of u plus c, or negative 1/2 times the ln of 6 minus t squared plus c. Okay, question 4 is a little bit different. If we made this u, right, so the variable w, it would have a derivative of 1. This certainly is not a multiple of 1. Okay, so we have to do something else. We have to simplify this first. And since we only have one item in the denominator and 2 items in the numerator, this would suggest that we split this into 2 terms, w squared over w and 5 over w, like that. Okay, so we take this, split it into our 2 fractions, and now simplify within each. This first fraction is just w. So now we have w plus 5 over w, and it's a sum. So we can just integrate each term separately with respect to w. So what would the integral of w be with respect to w? We would simply use this rule, okay? So it's a w and a dw, but the point is it's w to the 1. We're integrating w to the 1 here. Okay, so its integral is 1 over 2 w squared. 1/2 w squared plus 5 over w. When integrated, that's just 5 ln w. And then we have our constant. All right, so we had to split this one, and then after splitting it, we found that we had just an algebraic part here to integrate using our most basic integral rule, which you learned in your last math class. And this one here, of course, is perfect logarithmic form, just like problem 1 above. Okay. Let's continue. So let's look at this one. 2 terms in the bottom, so we cannot split this or anything as we did in the previous example. But what we can do is realize that the binomial in the bottom has an exponent of 1. So we can try our u substitution right away. This u substitution will work if a multiple of du is found in the numerator here. Okay, so let's figure out du. We take a sum of the derivatives. The derivative here is 2x plus, what's the derivative of sine? It is cosine. You read the derivatives right to left. The derivative of sine is cosine. But since this is 2x, we get 2 times the cosine of 2x. So that's du right there. And take a look at this numerator. It is certainly a multiple of this, right? It's 1/2 of this. Okay, if you like, you can common factor the 2 here, if that helps you see more clearly. The 2 is common factored from the front of the terms like this. All right, so now taking a look, we called the bottom u, and up top is all of this. That numerator is 1/2 of du. So we end up with 1/2, oops, Don't know why I put in that negative sign. You're gonna have to forgive me. Let's get rid of that, shall we? Okay, so the numerator is 1/2 of du, and the denominator is what we called u. Perfect logarithmic form. This is 1/2 ln u plus c. One half the ln of x squared plus the sine of 2x plus c. Okay, sorry about that. I had to answer the door. Let's continue on with number 6. I'm actually going to solve number 6 two different ways. So one way we can solve this problem is to recognize that sine over cosine is equal to tangent. We can use this identity because the angles here are the same. So this becomes 7 times the integral of tan x dx. And then we just go to our handy table and find that the integral of tangent is the negative of the ln of the cosine, in this case of x. So we'll get 7 times -1, -7 times the ln of the cosine of x. Like that. Okay, so that's using the identity here, sine over cosine is equal to tangent. If we don't use an identity, we can solve this problem by making u equal to that denominator, cos x. If u is cos x, then du will be the derivative of cos x. The derivative of cos x is negative sine x dx. So we'll have a u here, and of course it has an exponent only of 1. And then in the numerator, we have a multiple of du. So we will have perfect logarithmic form. In forming the derivative of cos x, remember you have to find cos x in the right-hand side. Okay, so this says the derivative of negative cos x is sine x. So that means the derivative of positive cos x would be negative sine x. Okay, so this saves you from using a derivatives table. You can read the derivatives right off of the integral table, provided you work right to left. Okay, so again, we have our 7 here. We have our integral sign. U is the denominator. But on top we have sine dx, not negative sine dx. So we have the negative of du in the top, the negative of du. So we put the du here, and the -1 can multiply by the 7 that is already out front. And then you can see that this is ln u. So we have -7 ln u plus c. What is u? U is the cosine of x. Okay, so we end up with -7 ln cos x plus c, just as we did in part A. So solving the same problem two different ways. Absolute value signs are there just to remind us that the logarithm of a negative number is not defined. But you can see sometimes I put them in and sometimes I don't. And it doesn't matter to me whether you use absolute value signs or brackets. as long as you do remember that logarithms are not defined for negative arguments. Okay, let's continue. This is problem 7. So let's think about it. If we call this bottom u, it does indeed have an exponent of 1. And so we would get logarithmic form provided that secant squared x resembles the derivative of the bottom. So let's give it a try. Let's let u be 4 plus 10x. And then what would du be? Well, it would be 0 plus whatever the derivative of tangent x is. So here's tangent x. Its derivative is secant squared x. Okay, so we have exactly u in the bottom and exactly du on the top. So we have exactly the integral of du over u, or ln u, once integrated. Okay, this is a definite integral, so as soon as we put back our u, I will do this so that we remember to substitute upper and lower limits and evaluate. So now we'll have this. The ln of 4 plus tangent pi over 4 minus the ln of 4 plus tangent 0. Okay, so we might want to work this out first. What is the tangent of pi over 4? What is the tangent of 0? And we can do this with our calculator, but again, make sure you're in radians. Okay, so let me try this for us first. Let's do the tangent of pi over 4. So we do the tangent of pi over 4, and we get 1. So that's a 1 right there. What about the tangent of 0? Well, that's 0. So now what do we have? We have the ln of 5 minus the ln of 4. Now, if you remember your logarithmic properties, this is the same as the ln of 5/4. Okay, which is fine for an answer, but we could work it out like this, right? Ln 5 minus ln 4 equals, okay, see the number that you get in that case, right? But we could also do it this way. The ln of 5 over 4 equals, and you should see that we do indeed get the same answer, and it is 0.223 approximately. And again, that would be to 3 significant digits. Leading zeros are non-significant. Okay, now number 8. 2 terms in the bottom, 1 in the top. So this is not when you can split this. You can split it if it's 1 term in the bottom, multiple terms in the top. What is the derivative of the bottom though? It would be 0 minus 3 times e to the 3x. So we have a multiple of that derivative in the top. This binomial in the bottom certainly has an external exponent of 1, so we know it's going to be logarithmic form. So let's call the bottom u. Its derivative is 0 minus 3 times e to the 3x. So we have a derivative of we have a multiple of du right here in the top. The bottom is u, What multiple do we have? Well, we have negative 5/3 times du. So negative 5/3 times du is what we have right here. Okay, so to work this out, you can take what you have here in the top and divide it by what you have here. Okay, so the exponentials cancel, the differentials cancel. Basically, you're doing 5 divided by -3 to get this factor. Okay, so the bottom is u, and the top was negative 5/3 times du. So now we have negative 5/3 ln u once integrated, and then put back the original binomial for u, and we're all done with problem 8. Okay, I will do one last example with you, and this is problem 9. Oh, problem 9 looks a lot like the problem we just finished. Very, very similar indeed. Okay, so let's solve it in the same way. The bottom is our u. That binomial has an exponent only of 1. So we suspect logarithmic form. It will definitely be logarithmic form if this 3e to the 6x dx is a multiple of what we write down here. Right here, we write down the derivative of this. It is 0 plus 6 times e to the 6x. So right here, we do indeed have a multiple of this. We actually have 1/2 of it. So 1/2 is the factor. du was in the top and u in the bottom. So 1/2 of du is in the top, u is in the bottom. Perfect logarithmic form. And we are now all done. And another way to get the 1/2, remember, is take what you have here and divide it by what you have here. Okay? The exponentials would cancel, the dx would cancel. What you have is 3 divided by 6, which is 1/2. All right, so that was 9 examples involving the exponential function. Remember, we did 8 examples. Sorry, no, that was 9 examples involving the logarithmic function. We did 8 examples in the last video involving the exponential function. And before that, in the first video, we did, I think, 10 examples involving trigonometric functions. So that means you have 10 plus 8 plus 9, 27 examples in total. And please try all of these suggested homework problems also. Okay, thanks very much. Have a good day.